Okay, in this section we're going to have a little bit of a biology lesson. We're going to consider the behavior of pigeons. So let's suppose we have a certain number of pigeons. Okay, and the pigeons are trying to make their nests. So they're looking for holes in the side of some sort of structure, a bridge, or maybe some mound of earth or something like that. So let's draw some holes. Okay, and each of the pigeons is going to fly into a hole and make their nest. So this pigeon might go here. This pigeon might go there as well. Okay, and I imagine this assignment as like a function. I imagine the domain to be the set of pigeons, and I imagine the codomain to be the set of holes, and the function assigns the pigeon to a particular hole. Okay, and you can see what happens, right? If there are too many pigeons and not enough holes, no matter how I try and spread the pigeons out, some of them are going to be forced into the same pigeonhole, right? And if on the other hand, I had more holes than I had pigeons, there's no way that the pigeons could fully occupy the holes. Let me draw that. So in this situation over here, the pigeons can fly into whatever holes they want, and since there are only 3 of them, there's no way that they're going to fill all the holes, right? And I'm not saying that they have to go into their own holes. We might have some doubling up as well. Just the observation that I want to make is since there are too many holes, then the pigeons can't occupy all of them. So nothing profound is being stated here, obviously, but we do get this sort of mathematical theorem about one-to-one and onto maps from this simple observation. Okay, so the pigeonhole principle is stated as follows. I'll prove the theorem at the end of this set of notes because there's going to be a little bit more powerful statement that we can make, and I'll just prove that, and then this one will follow directly from that one. So again, the setup was I had a function assigning each element of a domain set, which was understood to be pigeons, to a particular range element or codomain element, which was a set of holes. And if I have a function from x to y and the domain is too big, like there are too many pigeons, more pigeons than holes, then the pigeons must get forced into the same holes, right? There must be at least one hole that has more than one pigeon. So in the terms of one-to-one and onto, that means that f is not a one-to-one function, right? Okay, and if there are not enough pigeons to fill the holes, then f must not be an onto function. Okay, now a word about cardinality. The pigeonhole principle is stated in this section for finite sets, x and y. At the moment, we've only talked about cardinality of finite sets, so it's sort of understood from context that's what we're talking about. Both x and y are finite sets of pigeons and holes. But actually, the statement is perfectly valid once you develop a notion of cardinality of infinite sets. So we might be able to touch on that by the end of the semester, but once you get those infinite cardinalities developed, these two statements are still absolutely true. So that's kind of interesting. Okay, so let's use this mathematical theorem now to prove this kind of silly statement here. Let's prove that there are at least 2 people in Texas that have the exact same number of hairs on their heads. How would I go about doing that? Well, I go over to Google. Okay, and I just ask Google, what's the maximum number of hairs on the human head? And since everything on the internet is true, I can take this little observation here and bring it back to our discussion. All right, so it says on average you got 150,000 hair follicles on a person's head, but the entire adult body has something like 5 million. So like 5 million would definitely be a safe maximum for the amount of hair follicles on any person's head, in particular a person in Texas. Okay, now we go back over to Google and we ask what's the population of Texas. All right, and we have 28.7 million. That's in 2018. Something more than that now, probably. Okay, and now we set up a function. So let's let f from x to y, and I guess x is going to be the set of Texans, and y is going to be the numbers from, let's say, 1 all the way up to 5 million, let's say. Okay, so let's let f from x to y be defined f of little x. So little x is somebody living in Texas. Number of hairs on x's head. Well, since the cardinality of x is, 28 million-ish, and that's definitely bigger than the cardinality of y, which we're saying is 5 million. By the pigeonhole principle, this function is not one-to-one, right? So what does that mean? There are two different elements of the domain that get mapped to the same range element. So there are two different Texans with the same number of hairs on their heads. There you go. All right, here's a little bit more interesting, more mathematical example. Suppose you have a set of 6 positive integers, and each of those integers is less than 15. So that's like integers between 1 and 14. Amongst those 6 integers, I want to prove that there must be at least 2 different subsets of that set of 6 integers whose elements add up to the same number. Let me just do a little bit of scratch work so I get a sense for what the statement is saying. So A is going to be a subset of the numbers 1 through 14. And just to get like an idea, let's say A looked something like 1, 2, 5, 6, 10, 11. So just some selection of 6 numbers amongst these 14 numbers, yeah? Okay, but we want to consider A sort of at random. So A could be any selection of 6 numbers. What I want to show is, regardless of what A is, I can find at least 2 different subsets. 2 different subsets of A whose elements add up to the same number. So stare at this for a little bit and see if you can figure out a pair of subsets of this whose elements add up to the same number. Okay, well, I found a couple. So for example, this is a subset of A, right? It consists of the elements 1 and 6, and A has 1 and 6 in it. And its elements add up to the number 7, right? But there's another subset of A that also has its elements adding up to 7, namely 2 and 5. And this isn't the only pair. I can find, for example, the subset 110. 110 is a subset of A. Its elements add to 11, and 5, 6 is also a subset of A, and its elements add to 11. So in this particular example, there are several instances of 2 distinct subsets whose elements add up to the same number. And I want to prove mathematically, using the pigeonhole principle, that this always happens, regardless of what A is. As long as A has cardinality 6 and it's a subset of these numbers, you're going to have this happening. Okay, in order to do the pigeonhole, or use the pigeonhole principle, I have to set up a function. And like my first attempt, just based on how the question is phrased, I would think that what I'm doing is I'm assigning subsets of A to a number. So the input would be a subset of A, and the output would be an integer, which represents the sum of the integers in that subset. So I think like the domain of the function that I'm going to set up should be the power set of A, all of the subsets of A. And then the codomain would be all of the possible sums. Well, let's think about that for a second. The empty set is a subset of A, isn't it? And what are the sum of its elements? Well, 0, right? And so that's sort of the smallest possible sum that you could ever get out of a subset of A, not knowing anything about A. And then, there's sort of like all the possibilities in between. Like we saw a sum of 7 in this example, 11 in this example. And then I just want to think, what is the highest possible sum that you could ever see in a situation like this? Well, the highest number that you could ever see is if your A had in it the numbers 14, 13, 12, 11, 10, and 9, right? That'd be sort of the worst case. So let me put that also off to the side here. Like if A happened to be those numbers, these 6 numbers, then one subset of A that would give you the biggest sum possible would be A itself. And that sum should be, I think, 69. If I set up a function that goes from x to y and f of x, which is a subset of A, I'm going to call it B. That feels more like a subset of A. So f of B is the sum of the elements of B. Then the way that the pigeonhole principle would be useful is that the cardinality of x was bigger than the cardinality of y, and that would force f to be not 1-to-1, and hence you would have 2 different subsets of A that had the same sum of elements. Unfortunately, my attempt didn't work, because what's the cardinality of the power set of A? Well, A has 6 elements, so the power set has 2 to the 6 elements, and that's 64. And Y here has 70 elements, 69, 1 through 69, and then 0. And 64 is not bigger than 0. So this attempt simply failed. It doesn't mean that the sort of theorem isn't true. It just means my attempt wasn't so good. So this was attempt number 1. I'm going to try attempt number 2 now. Okay, let me be a little bit more clever about how I set up the domain and range of my function. I'm just going to deal actually with the non-empty subsets of A, because I know that the empty set has a sum of 0, and that's definitely not going to match any other subset of A as far as the sum of the elements go. So I'm going to change my domain to the power set of A minus the empty set. So this is all the non-empty subsets of A. And let's just observe here that the cardinality of X then is 63, right? It's all the subsets except for the empty set. There's 63 of them. Okay, and then let me consider what A looks like. Like, I'm not sure what the numbers in A are, but I'm just going to give them names so I can talk about them real quick. So let's give them variable names. Let's say A is A, B, C, D, E, F, and we've seen some possibilities up here for what those numbers could look like. And I'm just going to order them from least to highest. This is the lowest number, and this is the highest number in A. And then I'm going to think about all the possible sums for subsets of A. So let's just consider a subset of A, and let's suppose that we're thinking about non-empty subsets of A for a second. So B at least has to have one of these numbers in it, right? And the smallest number in the set is lowercase a, so the sum of the elements in B is at very least A, right? It's at least the value A. And because that's like the worst case, the smallest set you could possibly have would just be like singleton A, and the sum of those elements would be A, and A is the lowest number that's in there. Okay, what about at biggest? So let's think about how bad B could be. Well, if the numbers in the set, other than the lowest, were as high as possible, like 10, 11, 12, 13, 14, right? And we took the biggest subset of A possible, which is A itself, then the largest sum we'd be making would be A, whatever that number is, plus all these other numbers, just as an upper bound. So there's no way that the sum of the elements in a subset of A could possibly exceed A plus the sum of these numbers right here. Let's add these up. 60, like that. Okay, so right now I am considering the non-empty subsets of some random subset A that includes 6 integers from 1 to 14. And I've got a lower bound and an upper bound for the sums that could come out of that. So let me now try again. So y this time is going to be the possible sums that I can see, which is going to be whatever the lowest number A is, and then A plus 1, A plus 2, and then all the way up to A plus 60. I've decided that these are the possible sums that could come out where A is the smallest number that's in the set capital A. So my function now from x to y is still defined the exact same way. The function at a subset B is the sum of the elements. And now I think I get what I want. Let's look at the cardinality of the set y. Well, I know the cardinality of the set x is 63. That's the domain of this function. And the cardinality of the set y, well, look, it's A plus 1, 2, 3, 4, 5, 6, all the way up to 60. So that's 60 numbers there, and then one more. That's 61. Aha. So since the cardinality of x being 63 is bigger than the cardinality of y being 61, f is not a one-to-one function by the pigeonhole principle. So there must be 2 non-empty subsets of A, B1 and B2. So these are elements of the domain, subsets of A, such that f of B1 equals f of B2. I should say 2 different. And in other words, the sum of the elements of B1 is the same as the sum of the elements in B2. Okay, so there's the pigeonhole principle to give that argument.